Okay, let's try this again. Let's take a look at part 4, the final part of this unit, and inequalities. All right, everyone turn your attention to the front here. So, this is what it says in the curriculum, just to summarize. You're going to solve single variable inequalities with rational coefficients and solve the problems with this. To summarize, you're now going to be using these symbols: greater than or equal to, greater than or equal to, along with not equal to. Yes? Yeah. Well, that's what it says in the Manitoba curriculum. Yeah. But if we go back, that's exact. Yes, it is linear relations 4. Yeah. This is just the teacher speak you're seeing here. Okay, so let me break it down for you. Inequalities. Okay? Inequalities is basically a similar concept to what we've been working on. So in algebra, you can put together the pieces of algebra, the variables and the constants and all that, to form what they call algebraic sentences. The sentences you're used to are equations because they use the equal sign. But the other type of algebraic sentence is the inequality. So now, rather than an equal sign, you've got a few other symbols that you can use. The greater than, the less than, etc. So an inequality is one that uses one of those 4 symbols: less than or equal to, greater than or equal to. Okay? The equation uses the equal sign. With an equation, there's always one answer when solving it. But with an inequality, there's a range of answers now that you can use. Okay? Now, let's take a reminder of what those symbols are. Okay? We've talked about it before. But that means less than. That means greater than. Okay? I honestly think the easiest way to remember which is which is the one that kind of looks like an L, if you just kind of bent it a little bit, means less than, right? L for less than. That one doesn't look like an L, so it's greater than. There are other ways you can remember it. Some of your teachers might talk about the fish eating the other fish, etc. Boys? Questions? Yes.
I was taught, or this is what I thought.
Yeah.
Is that like, say one side's like 12, and the other side's like 6?
Yep.
So this side's 6. If this side is like smaller, it's like,
Yeah.
is this like bigger?
Yeah. If you think of this as an arrowhead, it's pointing to the smaller number, right? So like here you'd say 12 less than 5. The arrowhead points, that wouldn't work. Sorry, 6 is less than 12. So it's pointing to the smaller number. Yes, Simon? Absolutely. The whole alligator, when I was in elementary school, my teacher said it was a fish. Hey, if any of those work for you, great. But what I would like is if it's not working for you, if you're finding you're mixing those 2 symbols up, please try a new system. Okay. Now, the second you put the little line under it, it's combining 2 things at once. Now it's saying it's less than or it's equal to, or it's greater than or it's equal to. Okay? So that's a slightly different symbol. We'll talk more about it in a minute. If you draw a line through something like this, it just means not equal. Or you could even use ones, you're not going to do this very commonly, but not less than. Okay? The line through it just means not. Okay. So here's the concept to think about. What do we know about the can in these 4 diagrams? If this is a scale and these are kilograms, well, we know from the first one that 2 kilograms are less than the can. So whatever's in the can weighs more than 2 kilograms. What else do we know? Based on this diagram, 4 kilograms is heavier than the can or greater than the can. And then the final one, we know 6 kilograms is greater than 2 cans. Okay? So this is sort of that greater than, less than in action in the real world, where things are less than. If it was equal, the scale would be balanced, right? That would mean it would be equal. But we're dealing now with inequalities. So how do I solve these things? How do I do algebra with these? Well, basically, it's exactly the same as you've been doing. You just do the same concept, but there's one big exception. And I'll sort of show you what's going on here. So here's the inequality. 6 is greater than -4. Okay, so let's see what we could do with this 6 is greater than -4. Okay? If it's just like an equation, I can do anything I want to one side as long as I do it to the other side. So let's add 1 to both sides. Is it still true?
Yeah.
Because what is it? It's 7 is greater than -3. Okay, so that worked. Let's not add 1. Let's subtract 1 from both sides. We can do that. Subtract 1. Is it still true? What is it? It's 5 is greater than -5.
Excuse me.
Hello.
Could Rain Archer please come to the office?
Yes, she can.
Thank you.
So that's still true. Okay. What else could I do to one side or the other? Well, I could multiply it by 2, right? So let's multiply this side by 2 and this side by 2. Is it still true? 12 greater than -8. Yep. Could I divide both sides by 2? Divide this side by 2, divide that side by 2. Is it still true? 3 greater than -4. Seems fine. It all seems fine. Here's the exception. Let's put a negative number on this side. Yeah? What? Oh, sorry. This would, what would be 6? This, yeah, oh, yeah, you're right. Yeah, no, this would be -2, right? 4 divided by 2. And this would be 6 divided by 2, which is 3. Okay. I should have erased that one. That's why it was confusing. See, watch. If I erase this, then it should make sense. Right? 6 divided by 2 is 3. 4 divided by 2 is 2. Negative. Okay. Now, let's change this up slightly. Let's make this number negative. Is that still true? No. We got to put something over on this side that's greater than -6. What's something greater than -6?
-7.
No, that's actually less than that. Yeah. What's 5? Sure. Actually, let's put 12. Let's make it an even number. Okay? Now, if I add 2 to this side and I add 2 to that side, what's this plus 2? 4. And that's 14. So far, good. Let's subtract 2 from this side. -8 greater than 10. It's all good. Now, let's multiply this side by 2. -12 greater than 24. It's all good. Let's divide this side by 2. -3 greater than? No, 6. Right? Divide by 2. Right? It's all still working. But now, yes?
How is -6 more than 12 positive?
What? Oh, I'm sorry. Yeah, that's supposed to be, the symbol is in the wrong order. Of course, I did that on purpose to make sure you kids were paying attention. So good job. Okay. Now, thank you. Now, we added, subtracted, and multiplied and divided all by 2, and everything still was true. Here's the exception. Remember, I can do whatever I want to one side or the other. So I've got -6 less than 12, and I'll also use just 6 less than 12. I'll make one side negative, whatever. What if I divide this side, not by 2, but by -2? I can do that to both sides, right? What do I get? -3 is less than -6. Is that true? No. Now, similarly, I can multiply this side by -2. I'm drawing the X, which I shouldn't do, but let's do it anyways. -12 and -24. Is that true? No, it's not. So what we're seeing is the one exception to the rule. If you either multiply or divide by a negative. That's the scenario. If at some point in your solving of the equation you do that, to make it true, what do we have to do to make this true? flip the sign. That's right. And here, flip the sign. So that's the rule. Everything else is the same. So solving equations is basically the exact same here as it was when it was an equal sign, except for this case. If you either multiply or divide by a negative, flip the sign. So less than becomes greater than, and greater than becomes less than. I wrote it out like that to try and help you guys remember, just like when we used to stand on chairs and stuff. I didn't think it was a chair standing kind of day. But that's how you do it. Okay? You also see this in this chart, that's when it will become untrue. And it'll also be in your notes today. When multiplying or dividing by a negative, reverse the signs. Okay? So now I can solve inequalities the same way I solved equations. So I can move the x's around, I can subtract x's from both sides. I can get rid of the negative 2 by adding 2 to both sides. Okay? So now I'm here. 3x is greater than or equal to 6. Can divide both sides by 3. And my answer is x is greater than or equal to 2. And I can also verify it the exact same way. We've already done this. The only exception is that weird case. Now, the other thing that the curriculum expects you to do is put these on a number line. So the way you put it on a number line is not just a dot, but it's an arrow. Because the solution to that is anything that's 2 or above. So basically, this would be true as long as I picked any number that's either 2 or any number bigger than 2. So it could be 2 billion and it'll still be true. Yes? Well, it's any number that's either 2 or any number bigger than 2. Yeah, any number. Okay? If you have, now here's how you draw it. If you draw a dot that's filled in, that means it includes the 2. So that would be for the symbol greater than or equal to. If the symbol was just a greater than symbol, not the greater than or equal to, you're supposed to draw like an O, an open dot. Because the open dot means it's all numbers bigger than 2, but not actually 2. Okay, so that's what you're supposed to do. We'll see that in a minute. Okay, now, as I've said before, mathematicians are super lazy. So they tend to write things in what are called compound sentences. This is the compound sentence. It combines the words and or into the sentence. So this means 6 times n is less than or equal to 30. Right? It means or in the middle. It means 6 times n is less than 30 or 6 times n is equal to 30. I've combined these two things into one symbol. That's what the or means. What the and means is to combine more inequalities together at once. This is an example of a compound inequality. What this means is 3 is less than x and x is less than 8. Does that make sense? You read it that way. 3 is less than x and x is less than 8. Essentially what that means is x is somewhere in between 3 and 8. That's what it means. Okay? Could it be 3? No. Because it's anything, right? 3 is less than x. If that said less than or equal to, then yes, it would be that. This is also explained in your textbook through a few diagrams. So let me show you another example. Here's a compound inequality that says 100 is greater than or equal to 5x. And 5x is less than 200. Okay? It's red, as you can see here. It's that combination of and or in the compound inequality. Now, you can also put this on a number line. Here's how you do it. So let's read this out loud. Negative 4 is greater than x, and x is less than or equal to 0. It's a lot of words. But if I put it on a number line, it's the number negative 4 and the number 0. But notice at the spot where I put a negative 4, I use an open circle. Okay? Because the answer says it's greater than 4. But that means it doesn't include 4. But here it says it's less than or equal to 0. So it could be a 0. So that's why I filled in the dot right there. Okay? this could be a bit tricky. You're going to have to take some time to sort of process this. But that's what it means when you draw it on the inequality. Okay, that's it for inequalities. One last thing. A couple more suggestions for solving both inequalities and equations. These are the two ways you know. The one that I've been pounding in you guys' heads, the inverse operation, the add and subtract from both sides and divide and all that. There's also algebra tiles. You saw that you can use algebra tiles to solve stuff. Or you could modify them. But you know what? There are other ways to look at these problems. So I'm going to show you a couple other ways. Feel free to totally ignore what I'm going to say to you if this doesn't work at all. But one of them I kind of like, called the cover-up method, might work for some of you. Okay, so the most simple way to solve math equations is just guess and check. Some of you did that on some of the especially some of the word problems. You just did a lot of guessing and see if it worked. That's not an impossible strategy. It's just sometimes it takes a ton of time to do that. So if I've got this one here and I'm trying to figure out how I'm going to solve this, I could just guess. Well, maybe it's a -1. And then I could try to verify it and go, well, no, didn't work. Then I could try to guess that it's a 0. Well, no, 0 was too low. Then I could try and guess a 1. Oh, finally, I got it right, right? So, yeah, you could do that. You're going to give yourself more work, and you may never get it right, but guess and check sometimes is actually a way to, it's something to try. Okay. Another one is, rather than draw algebra tiles, why not think of this more realistically, like we did with the scale diagram there? Remember how I said back in the beginning that an equation is like a balance beam at the playground? Well, why not draw it that way? Why not say, okay, the squares represent x's and the cans represent 1. So it's supposed to be 4 x's and 2 cans and 3 x's and 3 boxes and 3 cans. So that I draw it all out like it's on a balance beam. Now, just like any balance beam, I could remove stuff from one side, right? So if I pull a box off this side, I better pull a box off that side to keep it balanced. So if I remove 3 boxes from this side, 3 boxes from that side, and then I remove 2 cans from this side and 2 cans from that side, what am I going to be left with? I'm going to have just a box equals a can, or an x equals a 1, and it's solved. Now that doesn't work with every sort of problem, but it's something to try. Okay, this one I actually think is a useful technique for some of you. It's called the cover-up method. Here's how it works. You actually use your finger or something to cover up part of the equation. So I would actually just cover up anything with a variable in it. The biggest possible thing. Like, for example, I could cover this whole side. I could go, what equals 300? 300, right? But then I just cover this part. What plus 50 equals 300? 250, right. Simon. Okay. So then what you do is the thing you just figured out, that 250, you write it down, and then you put an equal sign, and then you put what you just covered up on the other side of the equal sign. So I cover that, and I go, okay, what plus 50 equals 300? 250, that makes sense. So then I just rewrite it, and then I write what I covered. And then I could do it again. I could say 60 times what equals 250. Now again, this might be where you could stop and go, well, maybe I'll do that thing that Walks taught me before to try and get it there. I'm going to show you a harder example in a minute on how that works. Okay? So first, let's solve this inequality. I'm just going to do this one quickly. I'm not going to do it on the smartboard. Okay? So you'd use distributive property here. Remove the brackets, step 1. So I'd remove the brackets, and I'd get 2x minus 6 greater than 4x plus 2. Then I would combine like terms. Nothing to combine there, nothing to combine there. Then I would move all x's to one side. So I'm going to get rid of the 4x on both sides, rewrite it. 2x minus 6 is greater than 2. Then I'm going to get rid of I'm going to get all constants to the other side. So I'm going to get rid of the negative 6 by adding 6 to both sides. I'm going to be left with this. Watch this one. What do I do next? What do I do? By what? Wait a minute, if I divide by -2, what should I do? Flip the sign, that's right. I'm dividing by a negative. So at this point, when I get down to my solution, I flip the sign for it to be true. And I could verify that, and I could draw it on a number line if I wanted to. Okay? Now, here's an example where it's built into a word problem. Floppy disk for a computer, floppy disk, boy, that's an old word problem, must be kept at temperatures of 52 or below 10. Show an algebraic relationship for this, for the D, the temperature of the disk. Well, we know D has to be less than 52 and has to be greater than 10. How could I write that as a compound inequality? Well, I could say 52 is greater than D and D is greater than 10. Okay? Now, this is going to take some practice. Okay? I realize that some of you aren't grasping this right away. I can feel some of you. I can feel it. Some of you are shutting down right now. Okay? It's not going to help. It's not going to help you get these solved. Okay. Now, here's the cover-up one I wanted to show you. This is the last example. Okay? So I think I'm going to do this one on the smartboard. 5 plus 3x minus 1 over 4 equals 7. Okay? So let me just try this one on the smartboard. Okay. Was it 7? No, I've forgotten what it said. It was 4. Right. Thank you. 7's over here. That's 4. Okay. So here's how we're going to do it. We're going to cover up the thing with a variable in it. So I'm going to use this book. So I could cover the whole side here, and I could say, well, hang on. I could cover all of this, and I could say, well, what equals 7? 7, right? So that's not useful to me. But what if I covered all this? 5 plus what equals 7? Okay, so I write down the 2. And then I write down what I just covered up. Okay, it just got a little bit easier. Okay? Now, I could cover up all this, but that doesn't help. But what I could cover is the top half of this. Something divided by 4 equals 2. What would that be? No, not 2 divided by 4. 8 divided by 4. 8 divided by 4 equals 2. And then on this side, I write what I just covered up. Ooh. Now it's getting easier. Now, could cover the whole thing. That's useless. Wait, oh, sorry, this is minus 1, right? That's what I covered up. Now, I'm just going to cover that. Something minus 1 equals 8. What's the something? 9. And then I write what I covered up, which was 3x. 3 times what equals 9? 3. That's the cover-up method. It works if you're good at mental math, right? Because some of you struggled when I said, what divided by 4 equals 2? You're like, oh, 2, right? No. So it's kind of still showing steps, and we've got to a solution here. For some of you who've been struggling with writing down all the steps, this might be a possible solution method that you could try. It's known as the cover-up method, okay? So if you want to, give it a shot. I'm not recommending it for everybody, but you never know. Okay, so here's the animation that goes with that. Covered up. Look, I even made a sound for you guys. Watch. 5 plus what? Covered up. Covered up. That's my little thumb. You like that? That's like a little thumb. And we get the answer. X equals 3. Okay? So the key concepts here, that we're dealing with inequalities now, not equations. That's also something you need to do. And that one special exception, when dividing or multiplying by a negative number, flip the sign with an inequality. You can flip it with an equal sign too if you want, but it's going to come out the same. Right? Equal sign looks the same. No, never mind. Okay, and that's what it said in the curriculum. So I think we covered it. I think we're good. Okay, so let's get started on our fourth and final assignment for this unit.